This is question number 3. A 25 mm diameter shaft is pulled through a cylindrical bearing as shown in figure 2. The lubricant that fills the 0.3 mm gap between the shaft and bearing is an oil having a kinematic viscosity of 8 times 10 to the power of -4 and a specific gravity of 0.91. Determine the force P required to pull the shaft at a velocity of 3 meters per second. Assume the velocity distribution in the gap is linear. So in this situation, we have bearing and we have shaft here. So and then I hope you could imagine the mechanism of this thing. So if we want to draw the side view here, if we look from the side view here, so you need to draw it is something like this. So we have a shaft here, so and then we have a bearing here. So means that for example we have so we have a shaft around here, and this is the bearing, mean the hollow cylinder. So it will show something like this. Okay, so means that, so and then inside this area, so there is a lubricant with specific gravity and kinematic viscosity as mentioned in the question. So this is what you need to understand. So and then I would like to make sure that you could write you could draw the velocity distribution very well in this kind of problem. So in this situation, so we need to look at this situation. So means that this is the shaft surface. So and then this is the bearing surface. So the lubricant is filled between this shaft and bearing. So and then this shaft is being pulled in horizontal way like this. So means that if the lubricant inside this, so there are a lot of molecule, and then we focus on the molecule that stick on the surface here. So we found that this molecule is stick very hard on the surface, and then it gives us no slip condition, which U is equal to 0. So and then this molecule also stick very hard on the surface, but according to the question, this shaft surface is being pulled to the right direction. So means that this molecule, okay, it is not moving, but the surface of the shaft is moving with certain velocity. So we could say that relatively this molecule is moved according to the velocity of the shaft. So here, so it is said that the shaft is moving with a 3 meters per second. So means that the velocity of this molecule is actually equal to 3 meters per second. So and then because the velocity distribution is linear, so we could assume that the velocity distribution will something like this. So I hope you could draw the velocity distribution for this mechanism. And then if you want to draw the velocity distribution in this area, so again you need to understand that we have a shaft area here, and then we have a bearing here. So and then because the shaft is moving at certain velocity, so we have a velocity here. So and then here the velocity, the molecule is stick on the surface there. So we could draw the velocity distribution like this one. So please be careful when you need to draw the velocity distribution for any mechanism in mechanical engineering. So this is the question. This is the answer for question number 3. So you need to remember the equation for shear stress. Tau is mu du dy. So we have force which is equal to tau times A. So and then from these two equations, we could say that force is mu du dy times A. We just substitute the tau into this value. So and then because in the question we do not have any value of dynamic viscosity. However, the relationship between dynamic viscosity, which is mu, is equal to rho times nu. So nu is the kinematic viscosity. So we replace the value of mu here with rho and nu here. So and then we have an A here. So A is the area. So we could replace the A with 2 pi r and L here. So how to get the value of 2 pi r L here? So we need to see back the mechanism, the application that we have. So we found that the gap, okay, the gap is actually from here to here. So means that, okay, yes, shaft is actually longer compared to the bearing, but the condition where bearing and shaft give you a gap, a small gap of lubricant, it is only between this 0.5 meter only. That's why we need only to calculate the area of this one. We need to calculate the area of this one. So that's why in this calculation, we only calculate the circumference of the shaft. So the 2 pi r here is the circumference of the shaft. So and then the L here is the length, which is 0.5. So you need to understand that the length is actually the length that give a gap here. So according to this diagram, the length is 0.5 meter here. So we substitute all the value here, so we could get that the force need to pull the shaft is 286 Newton.